think we're ready to start. So hello there, my name is Alex Soderov. And first I wanted to say, thanks for having me at Ekoparty, and it's been a great conference, and I have been enjoying Buenos Aires a lot. So I think I will probably be coming back at some point. It is a really nice city, nice country. So this talk is going to be about reverse engineering cross-site scripting filters, and specifically about reversing them with a black box approach, which means reversing them without having the code to analyze. I have been working on attacking websites that I do not have the code for, because they're web applications that are proprietary, and unless you own the server that they run on, you can't really see what they're doing. So the approach that I have been using is to send various test cases, look at the results that I get, and based on that figure out how exactly the cross-site scripting filtering is being done. So why are we talking about this? Well, certainly there are a lot more. There are many other interesting areas to research, and I have done a lot of work on low-level exploitation and assembly, shellcode, that kind of stuff. But I do believe that web applications are the future. I don't know if we're going to have flying cars that can travel through time in the future, but we'll certainly have a lot of web applications. So hacking web applications is going to be a major part of what we're all going to do in another 5 years, perhaps. Unfortunately, or maybe fortunately, hacking web applications is very different from the standard type exploitation. And the big differences are, first, that the environment is completely different, but also that typically you don't have access to the code of the application. You can only interact with it remotely, so you need a very different approach. Cross-site scripting is the specific vulnerability that I'm going to focus on in this talk. Cross-site scripting is not that exciting. It's kind of simple. It's the equivalent of string copy buffer overflows in web applications, but it is a very good vulnerability to illustrate the concepts that I'm really talking about. So what makes web hacking so interesting? Well, a couple of years ago, web hacking was not that exciting because there was not much you could do by hacking websites. Maybe you could deface a website, get access to some porn website that normally would require you to sign up. But these days, there is a lot of very important information that is being stored in different websites. Not only that, but attackers have a lot more access to these websites, primarily because of Web 2.0. And what Web 2.0 means is that a lot of the content that you're going to see on these websites that you're attacking is actually user-generated content. And of course, the user in this case is the attacker. So we have attacker-generated content as well. We're going to talk about how this user-generated content needs to be processed to make it safe. This is usually done with cross-site scripting filters. So I'll talk about how these filters are typically built. This is very important to understand because before we start reversing them. Then I'll talk about the approach to reversing them that I've been using. And finally, I'll talk about a couple of cross-site scripting vulnerabilities in Facebook. I was hoping to be able to do a live demo, but unfortunately it appears that the bug that I wanted to use has been fixed since I last talked about it. So I won't be able to actually do it live. But if you're curious, there's a bunch more bugs in Facebook, so you can look for them and you can do your own demo. So Web 2.0. Web 2.0 has really changed a lot about what we see on websites and what kind of functionality we expect from websites. Nowadays, when you go to a web service, you don't just expect to get some content. You want interactivity. You want the ability to submit your own content, to send messages to other users, to tag pictures or whatever other content the website is dealing with. All of this requires very complicated functionality on the part of the website, and this is where a lot of the vulnerabilities this is what causes a lot of the vulnerabilities. A lot of websites have APIs that allow third-party applications and other websites to talk to them. Google Maps, for example, has APIs that allow any site to embed the map from Google into their own website. Many other services allow you to interact with them somehow. This also allows for the so-called mashups, which means taking the content from different sites and combining them together. And a lot of this content that is being pulled from different sites is not really that trusted. For example, if you're using an RSS reader, such as a Google reader or one of the other web-based RSS readers, the actual content that these readers are pulling from the blogs and displaying is not trusted. So if one of the blog authors inserts something that triggers a vulnerability, a cross-site scripting vulnerability in your blog reader, they'll be able to exploit you. So because of all these factors, we have a much larger attack surface than we had in the past. So there's a lot more vulnerabilities to be found. And also, I think the vulnerabilities are getting a little bit more complicated and hence a little bit more exciting for people like us to look for and to work with. So what is this user-generated content? What does the user-generated content typically consist of? You have the most basic one is just text. Any message board on the internet will accept some kind of text and display it. There's not much you can do with text in terms of exploitation. But a lot of users demand more rich functionality. They want to be able to insert images, perhaps some scripting content, multimedia, animations into their messages or posts or whatever other content they're putting up on the website. So to allow this, you have functionality like BB code and the Wikipedia markup, which allows you to do richer markup in the content that you submit. Some sites allow you to do limited HTML. They only allow certain tags. They do this to try to keep the content safe, but of course, if they fuck up and if they allow some tags that are not supposed to be safe, you might be able to exploit the service. And finally, you have sites like Facebook, which allows almost full HTML and even JavaScript to be part of this user-generated content, which then gets displayed to other users. This requires a very, very good filtering system to make sure that none of the HTML and JavaScript that you submit contains something that's unsafe. And this filtering system is what we will be exploiting later. You can also do, on a lot of services, you can do images, Flash, multimedia files, and these have tons of vulnerabilities in them. And they're especially useful if you actually want to attack the client. So for example, if you have a vulnerability in Flash, in the Flash plugin, you will be able to put a Flash movie up on Facebook or some other site, and then every client that goes there will be exploited. But in this particular talk, I'm only going to talk about, I'm going to limit it to cross-site scripting. So I'll deal primarily with the HTML based filtering that Facebook employs. So we've seen a number of attacks over the years that take advantage of these cross-site scripting vulnerabilities. You're probably familiar with a lot of them. We had a couple of worms on MySpace, Orkut. Skyline actually wrote a cross-site scripting worm in 2002, which exploited vulnerabilities in multiple webmail services and could jump from Hotmail to Yahoo Mail and back and forth. That was one of the first more interesting things that took advantage of cross-site scripting vulnerabilities. We've seen a lot of vulnerabilities in WordPress, blog software, and a lot of other services. Pretty much any kind of web application that you can imagine has had a cross-site scripting vulnerability at one point or another. And these are increasingly starting to get exploited. This is a very quick introduction to cross-site scripting in case somebody doesn't know exactly what it is. So what we have here is a little script on a website that takes a parameter called name, and we're passing a script tag as that parameter. When the web server receives the name, the script just outputs the text hello name. So if I say Alex, it'll say hello Alex. But what happens in this case is because the attacker put a script tag in the input parameter, the web script outputted the exact same bytes in the response. So now the response contains a script tag which says alert XSS, and this is going to pop up a message box that says XSS. If the attacker wanted to do something more interesting, then they'll replace the alert call with whatever JavaScript they want to execute. And this would allow them to take over the user session. So this is the basis of cross-site scripting. This is the basis of cross-site scripting vulnerabilities. The idea is that content that comes from untrusted users contains JavaScript, which gets loaded into the browser and interacts with the website where it is being displayed on. This is bad because the web security model assumes that a JavaScript or any other type of script that executes on one domain should be given access to everything within that domain. So it protects. It's okay, don't worry about it. So the web security model protects websites on one domain from accessing the content on websites on another domain. So if you have your online banking service open in one browser window, and you have Facebook or some other site open in another window, Facebook cannot access anything that's in the online banking site. But if we can inject JavaScript code into the online banking site, then that JavaScript code will be able to access a lot more. So what can we access? Well, we can read all the contents of the page that is being displayed. So all of the data that comes from that page can be read and transmitted to the attacker. We can also capture keystrokes on a web page. So while you're typing your password or any other kind of sensitive data, it can be captured. We can get authentication cookies, which might allow us to completely hijack the user session. And also, in recent times with XML HTTP request, we can actually do arbitrary HTTP requests to the same domain. This allows the evil JavaScript that we injected to completely impersonate the user. So basically, everything that a user can do in a browser, the cross-site, the script that we injected can also do. So this gives us, a lot of power. To prevent these types of vulnerability from happening, the web application designers and programmers had to do something. So what they typically do is they allow user-generated content, but they try to remove all the bad stuff out of it. So they try to filter it. Well, filtering seems like a pretty simple thing. You know that JavaScript is bad. So if you're writing a message box, if you're writing a forum application, a message board, it seems pretty simple to just say, well, we're not going to allow JavaScript, so we're just going to remove all the script tags, because this is where JavaScript is contained. It turns out that it is not that simple. The browser vendors have actually done everything possible to make it as hard as possible for us, or not for us, but for the web developers to filter JavaScript properly. First of all, it is not just the script tag that contains JavaScript. There are many other places where you can put JavaScript. There are many proprietary extensions to HTML that also allow scripting, which are supported by some browsers but not others. So when you're doing your filtering, you need to be aware of all of them. Browsers also accept all kinds of invalid HTML. and they try to sort of fix it up to make it displayable. Now, if you're writing a filter and you parse the HTML code in a different way than the browser parses it, you might get the two processes to get desynchronized. So the filter will think that something is safe, but the browser will actually execute it as JavaScript. And finally, some browsers just have bugs that allow us to bypass some of these filtering systems. So let's talk a little bit more in depth about these specific features that make it hard to build cross-site scripting filters. This is very important when it comes to reversing them, because we need to understand what kind of mistakes web developers could have possibly made, and then we can take advantage of those mistakes. Probably the simplest way you do scripting in HTML is with a script tag. Now this is fairly obvious, so pretty much any system is going to filter the script tag. But you can also put JavaScript in event handler attributes. You can put JavaScript in CSS content. Now this means that when you're writing a cross-site scripting filter, you not only need to parse HTML, you also need to parse CSS. And CSS comes with its own problem of incompatibilities and weird formatting and extensions. So everything that I said about HTML applies to CSS as well. You can also put JavaScript in URLs, and there were I don't think most of the major web packages suffer from this problem anymore. But a few years ago, it was fairly common that any message board that would allow you to post to link to images had the bug where when you put the URL for the image, instead of an HTTP URL, you would put a JavaScript URL, and that would lead to a cross-site scripting vulnerability. Now, this is pretty simple, so it has been fixed in most places, but it still shows you how hard it is to think of everything. The person who is writing the cross-site scripting filter needs to know about all of this and a lot more to be able to do their job properly. And anything they can miss can lead to an attacker being able to exploit the website. The other problem with HTML is all of the proprietary extensions to it. Most of them are Internet Explorer, and Netscape was also guilty of that back in the day, but Netscape is no more. So now Internet Explorer is the major offender there. So what we have is a number of different extensions, like the XML data islands, which Internet Explorer accepts. And these data islands allow you to take code that doesn't look like it's HTML and actually display it in the browser as HTML. So if you're writing a filter, you need to know exactly what the format is and how to parse it and how to understand it. The second thing about JavaScript expressions and attributes is a Netscape extension, which allowed you to put JavaScript in any attribute anywhere in HTML. I think this is probably not a terribly bad idea because it's fairly easy to filter, but again, it's something that you need to be aware of. Now, we don't really need to worry about Netscape 4 anymore, usually, but you still see these things with modern browsers as well. Conditional comments are another IE extension, and if you're writing a filter and you just assume that, oh, this is a comment, so it's safe, I can just pass it through, I don't need to worry about it. Well, this is not actually true, because you can have JavaScript and any other HTML code inside a comment, and Internet Explorer will execute it. So now the filter needs to filter comments as well. Also, this is one important thing to realize here is that browsers are a moving target. With any new version of the browser, you just have more and more, you have more features. So if you're a developer of the filter, you need to keep track of that. You need to keep up. Whenever a new browser is released, you need to make sure that the new browser did not introduce, some new feature or extension that you did not think of when you were developing your filter. So if you're looking at some kind of, at an old software package that was perhaps written a number of years ago and hasn't been updated since, you're probably going to find that that old package does not filter some of the new things that browsers now support. But everything that I talked about so far isn't actually that bad. I mean, you can just go, and most of these things are documented, and even the ones that are not officially documented are fairly well understood in the web application development community. So you will be able to find documentation and to figure out exactly what the different features are and what you need to filter. The thing that is much, much harder is dealing with the invalid HTML parsing. Browsers are very, very forgiving at what they accept. You can take HTML and you can like mess it up to a very large degree. And when you feed it into a browser, the browser will still try to fix it up and display what it thinks the author actually intended to display. So what I have here on the slide is an example of this. It's just one of the examples. We have a script tag with a source that points to a JavaScript file, and that JavaScript file will be executed by the browser. But that tag is actually invalid in many, many ways. For example, we have two opening braces in the beginning, which should make the tag invalid, but the browsers accept it. We also have a null byte inside the tag name. Internet Explorer, I'm not sure about Mozilla, but Internet Explorer for sure allows you to put these null bytes anywhere in the HTML stream, and it just strips them out. It ignores them completely. So you can have a null byte there in the middle of the script tag, of the tag name, and the browser will still run it. It also turns out that you can use a / as a separator between the tag name and the attribute instead of white space. You don't need to put quotes around the attribute names. You don't even need to close the tag for it to be parsed correctly by the browser. So when the browser sees this tag, it's going to fix up all of these problems and it's going to display it. But if you're writing a XSS filter and you're trying to parse the HTML, unless your parser handles all of these cases the exact same way, your parser might think that this is not actually a script tag. This is some other tag, or maybe it's not even a tag at all. So your parser has to, if you're passing through this data to the browsers, your parser needs to very carefully mimic the behavior of the parsers in the browsers. And again, this is a really complicated task because you have many different browsers you have to support, and you have many different versions, and the specific things that they fix up probably change from version to version. So again, that's something that you need to keep track of and maintain. You also have some browser bugs. Here are two examples of them. And I say that these are browser bugs rather than just very loose parsers, because there's no real reason for these things to be there, but it's just how the browser behaves. For example, in Internet Explorer 6, there is a weird thing about the way it parses invalid UTF-8 sequences. This was fixed in Internet Explorer 7. So UTF-8 sequences are usually 2 or more bytes, and the first byte in the sequence specifies how many bytes follow. If the and there are some rules about exactly what the bytes are allowed to be. So you could have a 2-byte sequence where the first byte says, this is a 2-byte sequence, but the second byte is not within the valid range, so it's actually an invalid character. So if you feed this to a parser that behaves, if you feed this to like Firefox and IE7 and other UTF-8 parsers, they're going to treat the first byte as an invalid character, and they're going to replace it with a question mark. But if you feed it to IE6, it's going to treat the first byte and the second byte as an invalid character. So if you look at the example there, we have a C0 byte followed by a quote. In Firefox, this is going to turn into a question mark followed by a quote. But in IE6, it's going to turn into a question mark followed by a space. This is because the quote byte disappears because the UTF-8 parser thinks that it's part of the character that is being replaced by the question mark. So why is this important? Well, when you actually run this through the parser, what gets the resulting HTML tree? In one case, it will contain a foo attribute and then a bar attribute. And both of these attributes are safe. They don't have any kind of JavaScript in them. But in Internet Explorer 6, we're going to have a foo attribute with slightly different contents, and then we're going to have a onload attribute which contains JavaScript. So the browser will parse it as a JavaScript event handler, and it will execute that JavaScript code. So if you're doing cross-site scripting filtering, you need to know about this, and you need to take it into account when you do the filtering so that Internet Explorer 6 users are not vulnerable to these cross-site scripting bugs. You have another interesting bug in Firefox versions before 2.0.0.2. This bug is in the parser, and it's white space handling. If you send it this body tag that I have on the bottom of the slide, we have the word onload followed by a bunch of non-alphanumeric characters, and then some JavaScript code. So in all the other browsers, this will be interpreted as a long attribute with a very weird name. It's like the name will be onload and then some strange characters. So the JavaScript will not be executed. But in Firefox, all of these characters, for some reason, count as white space. So when Firefox parses that HTML tag, it will see an onload attribute, and then it will see the JavaScript inside the onload attribute. So it will execute the JavaScript code. So these are just, this is in no way exhaustive. There are many other there are many other cases of vulnerabilities like this. I'm just trying to point out how hard it is to actually do the filtering properly. So now that you know all this, how are you going to build a cross-site scripting filter if you had to build one? Well, the first thing that people do is they try to write a string matching filter. So the string matching filter is basically a regular exception that looks for some stuff that is known to be bad and tries to remove it. So for example, over there we have a regular expression that removes the script tag. Unfortunately, string matching is a very poor choice for cross-site scripting filtering, and there are many possible ways you could bypass it. One of the funniest ones is if you do this thing, you have the script tag inside another script tag. So when the filter runs the first time, it's going to remove the first script tag, and if they only run it once, you're still going to have a script tag that gets allowed. So any kind of string matching filters, you actually need to run multiple times. And running it twice is not enough either. You actually have to run it until the output stops changing. Yeah, and it's kind of, I don't know, perhaps if you run it until the output stops changing, maybe the attacker can construct some HTML tags that turn this into an infinite loop. So the string matching filter just keeps running and the output keeps changing. So another big problem with string matching is that it uses a blacklist approach. So you remove the stuff that you know is bad, but perhaps you don't know all the bad things, so you might let something go through. So string matching is a bad idea. Don't do it. And if you find a web application that uses string matching to remove stuff, it's probably fairly easy to exploit, unless they remove like practically everything. If they only leave the letters from A to Z and strip everything else, then that's probably safe. But if they actually try to allow some tags but not other tags, then you can probably own that application. So a better way to do it, and this is what some of the more sophisticated web applications do, is they actually try to parse the HTML, and they try to build a complete HTML parse tree with all the tags and attributes as HTML nodes. So here we have a little HTML fragment, and when that fragment gets parsed, you're going to get a tree like this. You see the body tag there, which has an onload attribute with the text of the attribute. It also has a script tag and a p tag. So once you build that kind of tree, you can iterate over the tree, you can traverse the tree, and you can remove all the specific things. And you will know that the onload attribute is called onload, and there is no way to fool you, because right. So this is a much better way to remove things, from the HTML. But there's still one problem with it. Once you remove the elements from there and you start outputting them, if you just pass all of the text through, if you output it without re-encoding it, you might actually output something that you did not intend to output. So, for example, if the text of one of the attributes contains some angle brackets and maybe some quotes, and you just output that text directly, those quotes might terminate the attribute, and then you might escape from the attribute and start building another tag, and this would be bad. So what you need to do, when you build a cross-site scripting filter is, when you build this dump parser, you also need to do the output and canonicalize everything that you output. So, for example, when you're outputting an attribute, you need to escape all the special characters that need to be escaped in attribute values. The same goes for tag names and just all the regular text. And this escaping is much, much easier than actually trying to filter out the non-escaped stuff. So if you do this, you're going to be in a pretty good shape. And Facebook actually does this. So, they've thought about it, at least to some extent. Now, the final thing that you need to try to do, if you can, is use whitelisting instead of blacklisting. The problem with blacklisting is that you remove the known bad stuff, but if you miss something, if your blacklist is not complete, then you still have a vulnerability. Whereas with whitelisting, you're only allowed the things that are known to be safe, and unless for some reason they change, something that used to be safe turns out to be not safe in a future browser version, that's the only case where you're going to run into a problem. This is one of the cases where Facebook fails. They do use whitelisting for some parts of their filtering, but not all of them. And some of the vulnerability, there's some vulnerabilities that are related to their blacklist not being complete. So now that we know how these cross-site scripting filters are built, let's look at how an attacker can look at a filter and reverse it without actually having the code. Now, I'm not going to deal with the normal type reversing because that's too simple. Like, everybody knows how to do it. You load the file in IDA and you look at the code, you read it, you understand how it works. If you have a remote web applications that you don't have access to, now things get much more interesting. You cannot just read the code. You cannot read the binary either. Fuzzing would be one way to find vulnerabilities there, but in a lot of cases, you can't really fuzz without, calling attention to yourself. you can't send, or you're just going to overload the application. Maybe you can send 100 requests per second, which is quite a lot of requests. But if your fuzzer is kind of stupid and it needs, hundreds of millions of requests until it finds a bug, then it's going to take a long time. And also, if you're doing this on a site that doesn't actually like to be fuzzed, they might have, they might just block your account. They'll notice that you're sending too many requests. So it's going to look like a denial of service attack. And it might actually cause denial of service, which is something you probably don't want. So you need to find a way to do it by sending data and inspecting the output, but without sending too much data. You only want to send like a very limited number of test cases. So this is what I call black box reversing. Come on, yeah. So here we have this is the basic approach to reversing these filters that I've been using. So first, you try to think about how would the filter work, if I had to write it. This is why I did the previous part of the presentation where I talked about how these filters are actually built. So you come up with an initial model of the filter. Then you generate some test cases to run through the filter. You run them through the website and you see what the results are. Once you get the results, you check whether they match your model. If they match your model, then everything's good. If they don't match your model, then you update the model. And you keep doing this iteratively until you have like a complete model. Perhaps it can never be 100% complete, but it can be large enough to cover all the cases that you're interested in. For example, you might start by trying to figure out whether this is a string matching filter or if it's a HTML parsing filter. The way to do that is, there are many ways to do this, but one of the sample test cases could be if you can find a place where the filter makes decision based on data that it hasn't seen yet, like data that's forward in the stream, then this means that they're not just parsing the stream linearly. It means that they're loading the stream into a parse tree perhaps, and then looking at whole parts of it. So this is how they can take into account, future elements. So that's one way to do it. You can also just find, if you find some vulnerabilities, there are, for example, the string matching vulnerability that I described, where you have a script tag inside another script tag. That's, if you find that the filter you're looking at has that vulnerability, you know that it's a string matching filter. It cannot be a HTML parsing filter. So you can have a set of these test cases that you send, and based on them, you kind of have a binary decision tree. So if this test case returns, true, then the filter is one of those. If it returns false, the filter is one of those. So you can sort of narrow down the type of the filter, and then you can actually start looking at the specific implementation of the filter. Here's an example of how to do this. This is a little Ruby script that generates a test case. It iterates through all the bytes from 1 to FF, and it generates a p tag with that character and then followed by an A. So when you send this to, and let's say that the filter you're reversing, you know that the filter removes the tag with the name A. So when you send this test case, you'll see that some of the A attributes, some of the attributes have been removed, but others have not. This is because the characters that are counted as white space in the filter will lead to the filter parsing this as a attribute and then removing it. But the characters that count as a part of the attribute name will change the attribute name so it's no longer A, and it will no longer be filtered out. So you will see it in the output. So this allows you to figure out which characters count as white space and which characters count as part of the attribute name. And down there we have an example that actually ran through Facebook. So the tab characters and the new line characters and the quotes count as white space in that case. And then all these other characters, the letters, numbers, the colon sign, they all count as part of an attribute name. So this is something useful to have because it allows you to update, to have an accurate model of how the filter behaves, like how exactly it does the parsing. And once we have that model, actually before that, small diversion, I have this script that I wrote. I called it refilter because it reverse engineers filters. This script is, it's a little Ruby script that generates a bunch of these test cases. And so the test cases are not random. I have specifically designed them to give you some kind of useful information. And then it has a modular system, so you can plug in modules for different applications. And I have a module for Facebook, and the module implements all the functionality that's needed for sending data to Facebook and receiving the result and understanding, basically interacting with the web service. So you can have different kinds of web services, web applications, and the module handles all that application-specific stuff. And then the test generators just generate different types of test cases. So I have this, it's up on my website. I'll give you the URL if you want. So it's a fairly simple script. It's more of a proof of concept or a prototype. It doesn't actually do that much, and you can probably write something similar fairly quickly. But I think it's just a good example of how these things can be automated. I think the best part about the refilter script is that with a simple command, I can tell it to run all of the test cases against Facebook and collect all of the information in sort of in a directory in a bunch of output files. And a week, so I actually did this. I reported a bug to Facebook some time ago, and before I reported the bug, I had, I ran my test and I had this output directory, and then after I reported the bug, I just ran the single command that ran all the tests again, and it gave me another set of output files, and then I just diffed the output files to see exactly what they changed in order to fix my bug. So I did this, and I found that they didn't actually fix the bug completely. They only fixed it in one of the cases, but they missed up another one. So an hour later, I had another bug report for, hey, you missed this, you're stupid. Yeah, I didn't actually tell them they were stupid, but I think they got it. So what do you do once you have the model? Well, once you have the model, you can fuzz it locally. That's actually kind of fun. You can implement a filter that behaves the exact same way, and then you can run your fuzzer against your local copy. And if your local copy is accurate enough, you might actually find some bugs through fuzzing, and then you try them against the real filter that's sitting remotely on the web server, and maybe the same bug will be there too. That's a fun thing to do. If you actually want to, use your brain more, you can, more than just simple fuzzing, you can actually build a grammar for all the valid output that the filter allows. And then you can also build a grammar for the JavaScript that the browser accepts. And when you have the two grammars, you can compare them. And if you find any valid sentence that's valid in both grammars, this means that you found something that can go through the filter and the browser also accepts it. And now, how do you build a grammar for what the browser accepts? Well, you can use something very similar to the refilter script. You can actually build a bunch of test cases, feed them through the browser automatically to get a complete a complete list of everything that the browser accepts. So there are two. Now this is more conceptual. I have not actually. I mean, this is how I think about it when I do it, but I've only done it manually. I have not actually automated this process. And I think it will be a very interesting research project for somebody to sit down and figure out how to automate it. I'm pretty sure that you can automate the step that extracts a grammar from a remote filter. You can automatically generate these test cases and then update your Lexer and your parser models based on the results that you get. Also, comparing the two grammars is something that can be done automatically. So, if somebody wants to do if some graduate student somewhere wants to do a research project on it, I think this will be kind of neat. But I think it will be quite a lot of work to actually do it. So now that we covered sort of the conceptual model of how you reverse engineer these cross-site scripting filters, I'll just give a simple example of finding these bugs in Facebook. This whole work started just because I joined Facebook and I was looking around and I wanted to see if I can find any vulnerabilities in it. So I just played around with it a little bit. So Facebook allows you to create third-party applications that interact with their platform. These applications have the ability to create content that gets displayed to the users. Now, this potentially leads to cross-site scripting vulnerabilities if that content is not filtered properly, because the third-party applications come from, anybody. Like anybody can just sign up to be a Facebook developer and create an app. So Facebook has this special version of HTML that they call Hbml. It's basically the same as HTML, but some of the tags are not allowed, and there's some restrictions on style sheets and scripting. They also allow
we are delayed and we have to rush. We have to accelerate this presentation because artists that are waiting for use the stage. So I have to say sorry, and I apologize, but I have to, I don't know, maybe 10, 15 minutes.
Oh, I can finish in less than that. I'm almost at the end, actually.
Oh, I'm sorry. Well, that's it, because I have like 20 people saying like,
okay. All right, so this is the final part of the presentation, so we're almost at the end. So I'll wrap it up quickly. So Facebook allows the applications to create this Hbml content. It also allows the applications to do scripting using something they call FBJS, which is a sandboxed version of JavaScript that they run inside the browser, but they implemented a sandbox, so the JavaScript cannot actually do anything bad. Now, that had a bunch of, I haven't looked at the JavaScript implementation specifically, but there was a post on Full Disclosure some time ago that listed like probably 10 different bugs in their JavaScript sandboxing that could be exploited to escape from the sandbox. So there are bugs there too. Here's the basic diagram of how this works. The third-party application is actually a web app that runs on some other server somewhere, like on my own server. And the browser requests the application page from apps.facebook.com, which serves as a proxy. And it requests the Hbml from funapp.example.com, if that's where the application lives. The Hbml gets processed by the proxy, and it gets turned into HTML after all the filtering is done. And then that HTML goes to the browser. So if there's any vulnerability in that filtering that happens in the proxy, we'll have a cross-site scripting bug. So I used my refilter script to run my test cases through Facebook. I had the script running on the same host where my application was. So the script would generate an HTML file. and then I would send a request through Facebook for that file. Facebook would get the file, translate it, do the filtering, and then send me the result. So basically, I could, I controlled the input for the filter, and I could see the output of the filter. And with that, I found a couple of bugs. One of them was the invalid UTF-8 bug, which I described how it worked a few slides back. If you had invalid UTF sequence, for example, one that starts with a C0 byte, Facebook would it would not filter it, so it would think that it's just part of a normal attribute and let it through. And the problem there is that Facebook claims to send valid UTF-8, but they don't actually enforce the UTF-8 validity. So an application could send them invalid UTF-8, and they'll just pass it through instead of parsing it and properly handling it. So I reported this to Facebook, and they fixed it. And this was the bug where they fixed it, but they got it wrong, so I had to tell them about it again, and then they fixed it completely sometime later. The other bug that I found, or one of the other bugs that I found, it affects only Firefox versions before 2.002. That was the version that allowed all of these weird non-alphanumeric characters in attributes, and it treated them as white space. So see how the presentation sort of comes back together? All the stuff that I talked about earlier, it's actually relevant. One of the, when I reversed the filter, I found out that Facebook allows the colon as part of the attribute name. And this is probably done because in HTML, you have these namespaces, and the colon is between the namespace and the tag name. But they also allow it before or after the tag. So I could do an image with onload colon equals and then some JavaScript code. So when their filter runs through this, it treats the colon as part of the name. So it sees an attribute called onload colon, and that's an OK attribute. It's not on the blacklist, so they allow it through. But when Firefox sees that same attribute, it treats the colon as white space. So Firefox sees an onload attribute, and then it executes the JavaScript code. In June, it wasn't fixed, but I was actually helping to demo this now, but it appears that they have fixed it since then. So unfortunately, I can't do a demo of that. But there's more, so if you look for them, you'll find some probably. So in conclusion, what does this all mean? Well, it means that doing web applications is really, really hard. I already went through all the difficulties with cross-site scripting filters. This doesn't even, doing web applications is hard because of many other things too, non-security related. Dealing with all the incompatibilities between the browsers is another really hard thing. But I don't really care about that because I'm a security guy. And for security, the web security model that we have is based on the idea that each web server sort of sits on its own, and all the content that that web server serves is actually trusted because a trusted user wrote it, and then the web server is serving it. The idea of dynamic content that aggregates untrusted information from other sources or information that came from the users, that idea just did not exist when the web security model was being created. So it just doesn't deal with that at all. And we've had to hack the web security model to do the things that we want to do now with web applications. The undocumented browser behavior and just the differences in browser behavior is another big problem. A major other thing that I think is contributing to these problems is the fact that the programming languages do not support HTML as sort of a native data type. If you want to manipulate HTML streams, it's very hard, and most people just do it by treating them as strings and concatenating different strings. And similar to the way the C language does not have a string type as a native data type, and this led to many people using all these other libraries for doing string manipulation and modeling the strings as just arrays of characters. This led to a lot of vulnerabilities, the string copy bugs, all these other buffer overflows. In the exact same way, now with web applications and the frameworks that we have for developing web applications, a lot of them are treating this HTML content as strings, which is not what it actually is. And because of that, we see a lot of problems where people just concatenate strings and don't filter them correctly, or they try to filter them with regular expressions, just like they would filter strings. But because they're not strings, this leads to problems. And finally, I talked about Blackbox reversing in this talk. I think it's an exciting new thing. It's not new. People have been doing it for a long time, but now with the development of web applications, you actually have to do it a lot more than you did before. Most web applications that are out there, that's the only way you can reverse them, unless you can actually own the server and get the source. But that's harder. So I think we need much better tools, processes, and automation around reversing web applications remotely. And I'm hoping to sort of push the community towards that and get more people thinking about these problems and see what we can do. So that's it. If you have any questions, maybe you can ask now if we have time, but we probably don't have time. So if Federico tells us to go, we can go. Do we have time for question? If somebody has any questions, you can ask now. Yeah? Hmm? Feedback fuzzing. Well, there's definitely feedback, but I'm not really fuzzing because I'm not trying to. The idea of fuzzing is that you send out input that's basically random, or at least randomly malformed. In this case, I have focused on getting the smallest possible set of test cases that I could send. And all these test cases were manually created and optimized. And the idea is to get a binary decision tree through which you can traverse based on the output. So, it is similar to fuzzing, but it's not exactly the same thing as fuzzing. And the main reason I wanted to do it is because I wanted to understand how the filter works, which is reversing. And I wanted to do it in a way, I wanted to do it without having access to the filter code, which is why I call it black box reversing. But I agree that it is very similar to fuzzing conceptually. Mm-hmm. What? Virtual JavaScript? Oh. Well, you don't actually need a. Certainly you can run a JavaScript interpreter in a virtual machine, but you don't actually need a x86 virtual machine to do that. You can probably instrument the JavaScript engine inside one of the browsers, or even run it outside of the browser separately as a filter. And once you instrument the JavaScript virtual machine, you'll know exactly what it's seeing. But again, you have a problem there. If you do this with, probably you're going to do this with the Firefox Java runtime or JavaScript runtime. But when you do this, you're going to miss all the things that Internet Explorer is going to do.